everyone. Welcome to today's class. We are going to be looking at GCE questions on refraction of light. Okay, so we are going to be explaining refraction and the leading question of refraction using GCE past exam questions. All right. Now, what is refraction? Refraction is the bending of light when it passes through a boundary between two media, or we can say that refraction is the bending of light at the boundary between two media of different densities, thereby causing a change in its direction. How do I mean by that? If I have this is a refractive, let me say this is a glass block, okay? This is air and this is what? Glass. Now this is normal. Normal is a line that is perpendicular to the reflecting surface. When light pass through here, this is my normal N. When light pass through from air to glass, because these two are different medium and they have different densities, so there will be a bending at this boundary, and that bending is what is said to be refraction. Okay, so this bending comes this way. The angle between this is what we call the incident ray, and this is what? Refracted ray. Okay, the angle between the incident ray and the refracted ray is what is said to be what? The angle of incidence, I, right? And the angle between the refracted ray and the normal is said to be what? The angle of what? Refraction. Is that clear? All right. So let me do a recap. Whenever light passes or travels from one medium to another of different densities, there is what to call bending. And that bending occurs at the boundary between these two media, and that is what is said to be refraction. Now, if I extend this incident ray, I'm going to see we can calculate our angle of what? Deviation, right? How can we calculate our angle of deviation? From the mathematics knowledge, we can say that vertically opposite angle, they are what? Equal. That means I is equals to R plus what? D, right? And if I'm asked to find the angle of deviation, I'm going to say that the angle of deviation is equals to, I'll carry this R to the other side, that is I minus what? R. Is that clear? So what am I trying to say? I'm trying to say that for me to get the angle of deviation through this glass, I'm going to say angle of deviation D is equals to angle of incidence minus angle of what? Refraction. Is that clear? And there is a law that is governing this, that is the laws of refraction. We have two laws. The first one says that what? The incident ray, the refracted ray, and the normal at the point of incidence all lie on the same what? Plane. Let me say it again. The incident ray, the refracted ray, and the normal at the point of incidence all lie on the same what? Plane. Right? Now the second law states that what? The ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for a given pair of media. Let me do a recap. The second law states that what? The ratio of the sine of the angle of incidence I is equal to the sine of the angle of refraction what? Let me go again. The ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for a given pair of media. Okay? That means sine I, which is angle of incidence, divided by what? Sine R is a what? Is a constant. And what is that constant? Sine I over sine R is a constant. That constant is called refractive index, and that is only when light is traveling from air to what? Glass. So if I say ANG, I mean that light is traveling from air to what? Glass. From air to what? Glass. Is that clear? All right. All right. So apart from that, we still have other relationship connecting this n, which is the refractive index. So we can say that n is equals to sine I over sine R, okay? Then is equals to velocity in air, then velocity in glass, okay? We can also say the speed in deep water, then this. All right. We have wavelength in medium 1 divided by what? Wavelength in medium 2. Okay? Now, all this medium is when light is traveling from air to what? Glass. So if I write ANG, 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 okay? It means the light is traveling from medium 1 to medium 2, or from air to what? Glass. Is that clear? All right. All right, so I'm going to be looking at a few examples using these leading formulas to solve under refraction. I am going to be concentrating on the GCE exam questions, past exam questions, okay? So if you're preparing for this coming GCE by next month, December 2024, or you're preparing for the first coming WAEC, so you're going to stick to this class so you can understand how you can apply questions, okay? say this is number 1. All right. So for us to be able to solve this, we are going to analyze it to see what we have. Okay. All right. So let's solve. A ray of light passes through glass of refractive index 1.50, which is also a constant. If the speed of light in vacuum is 3.00 times 10⁸ meters per second, determine the speed of light in the glass. All right, in this type of question, what are we expected to do? We are giving the refractive index of glass to be 1.50, and we are giving the speed of light in air, that is in vacuum. You can tag it as what? The velocity in medium 1, and it's giving us 3.00 times 10⁻⁴ 8 meters per second. And I asked to calculate the velocity in the second medium, that is what? The medium 2, right? Now, what are we expected to do? We are going to use our formula, knowing that the refractive index of glass, Ng, right, is equal to what? V1 over what? V2, right? Now, from what we have the refractive index to be 1.50 is equals to, my velocity in the first medium is 3 times 10⁻⁴ divided by what? V2, right? So I can say cross multiply by saying that this is over 1 cross multiply. Okay? So I can also say that V2 is equal to 3 times 10⁸ divided by what? 1.50, right? All right. So if I divide it, I have 3 exponents 8 divided by what? 1.5. So my answer becomes 200000000, okay, which is the same thing as what? 2 times 10⁸ meters per second. That is the velocity of light in the second medium. Is that clear? Right. let's look for more examples to solve. All right. Looking at this question, a ray of light is incident on a body X, as shown in the diagram below. What is the refractive index of the body? Now, if you must remember, for us to solve this refractive index, we are given two angles here. This is what we say to be the glancing angle, and this is also a glancing angle on this interface, right? We are supposed to find the angle of incidence I, and also find the angle of refraction what? R. Okay? Then for us to do that, what are we going to do? We should know that this is a normal, and normal is what? Perpendicular line to this reflecting surface. That means our normal is 90 degrees. So this is 90 degrees. Okay? And this is also 90 degrees. And if you go by that, we are going to find this angle here, which is angle of incidence. Okay? By saying that I plus 30 is equal to what? 90. Alright? Because right angle or angle of right angle is what? A right angle. Sorry, we can say that this is a right angle triangle, which is angle of 90 degrees. Okay? So this is equal to 90 degrees. So this is what? I will take this to the other side. 90 minus 30, I'm going to have 60 degrees. Okay? So my angle of incidence have gotten to be 60. I can get my angle of refraction by saying that R plus 50 is equal to what? 90, right? R is equal to 90 minus what? 50 is going to give me 40 what? Degrees. Okay? So for me to solve for refractive index, I should remember that M, which is refractive index, is equal to sine I over sine what? R, right? So what do I mean by that? I will say, what is my sign what? My sign I. It's either I solve it or I bring them together. So I can decide to solve it this way. Solve it this way by saying that n is equals to sine I over sine what? R, right? So let's go. What's my sine I? My I is gotten to be what? 60 divided by my R is gotten to be what? 40. So that is sine what? 40. Now I'm going to divide and get what I have. Sine 60 is a constant and is given as 0.8660, then divided by sine 40 is given as 0.6427. Then by the time I divide it, I will say 0.866 divided by 0.6427. Okay, I will have my refractive index to be 1.347. Okay, and you must not forget that this refractive index of glass is constant. Since it is constant, you can as well find the unknown, right? Yes, you can as well find either the angle of incidence or the angle of refraction. Now, if the refractive index of glass is known and we are given the angle of incidence, we can use that medium to also solve for the angle of refraction or even the angle of what? Deviation. Is that clear? Right. All right. Let's go to the next one. This is question 3. All right. Let's look at what we have in this question. An electromagnetic wave of frequency 5.0 times 10 raised to power 14 Hz is incident on the surface of water of refractive index 4/3, taking the speed of the wave in air as 3.0 times 10 raised to power 8 meters per second. Calculate the wavelength of the wave in water. All right. Now, for us to do that, there is one thing that we must put into play. Let us set our parameters to see what we have. Okay. All right. So we have the frequency. We have the frequency. The frequency. All right. To be 5.0 times 10 raised to power 14 Hz. We have the refractive index to be 4/3. Now we have the speed in air, I can call it V1, which is 3.0 times 10 raised to power 8 meters per second. We are asked to find what? The wavelength of the wave in water. Wavelength is what? Lambda 2. All right. Now, for us to be able to do that, we are given the refractive index, yes? We are asked to find the wavelength in medium 2, and we are given the speed of the wave, that is in medium 1. But we don't even have the wavelength in medium 1. So we need to get the wavelength of this wave in medium 1, okay? Now, following this relationship, that V is equals to F lambda, right? This becomes the speed in medium 1 and the what? Wavelength in medium 1. Is that okay? All right. So what are you going to say? You are going to find this. Wavelength in medium 1, that becomes V1 over what? F. Right? So let's go. What's my V1? That is 3.0 times 10 raised to power 8. Okay, you don't need to put the units. You say divided by what? F. That is 5.0 times 10 raised to power what? 14. Is that clear? All right. So let's work it out. You see what we have? 3 exponent 8 divided by 5 exponent 14. What do I have? I'm going to have 6 times 10 raised to the power of minus 7 meters. Now, this is the wavelength of this wave in medium 1. And we are using the relationship connecting the refractive index and the wavelength. So that is N is equals to wavelength in medium 1 over wavelength in medium what? 2. Is that clear? And we're looking for wavelength in medium 2. Okay? We have used this relationship to get the wavelength in medium 1 with our refractive index, so we can solve. All right? So I will say 4/3 is equals to what? The wavelength in medium 1, that is 6 times 10 raised to power minus 7 divided by what? Wavelength in medium 2. Right? So for me to make it the subject, I will say lambda 2 is equals to 3 times 6 times 10 raised to the power of minus 7 divided by what? 4. Right? So work it out by saying 3 times 6 exponent minus 7 is equals to 1.8 times 10 raised to the power of minus divided by what? 4. Okay, if I divide by 4, my answer is going to give me 4.5 times 10 raised to the power minus 7 what? Meters. Now let me do a recap. We are given this question and we have the frequency to be 5.0 times 10 raised to power 14 Gs, and its incident on surface of water of refractive index 4/3. Then taking the speed of light, which is constant, to be 3.0 times 10 raised to power 8 meters per second. Calculate the wavelength of the wave in what? Water. And water is the second medium, okay? We're looking for the wavelength, that is lambda in medium what? 2. But from the question, we are not giving the lambda in medium 1. So what we are going to do now is to do what? Is to state all these parameters and use this, because V is equals to F lambda. So we are going to use it to get the wavelength in medium 1. Of which, once we get it, we now use this formula of refractive index and put in what we have to solve our question. Is that clear? All right. So using what we have, lambda 1 is equal to V1 over what? F, which is equals to, what is my lambda? What is my V? 3.0 times 10 raised to power 8 divided by 5.0 times 10 raised to power what? 14. Okay. By the time I divide, I got this. Is that clear? All right. So using this formula of refractive index, I have n is equals to lambda 1 over lambda 2. Substituting into what we have, we got an answer to be 4.5 times 10 raised to power minus 7 meters. Is that clear? Okay. Now, one thing you must know is that as light moves from one medium to another, frequency remains what? The same. Frequency does not change. Is that clear? All right. Justina, you're welcome. How are you today? Okay, this topic is under refraction. Refraction of light. King's Match, you're welcome. If you are just joining, give it a thumbs up, okay? Let me just set a poll. All right, so let's go into another part of it. explain this concept, okay, you should know that refractive index is also related to real and apparent depth. How? If you place a coin inside a bowl filled with water, okay, where are you going to see the coin? You're going to see the coin where it's supposed to be, which is the bottom part of what? Of the water. Is that okay? But when you look through to see the depth of the water, to see if you can be able to see that pin, it appears to be what? Apparent. It appears to be shallow. It appears to be here on the surface of water rather than being at the bottom. Why is this so? Because light has traveled from one medium to what? Another, and which is the concept of refraction. Okay, when light move from one medium to another of different density, of course we know that water is denser than air, glass is denser than air, so whenever light move from one medium to another of different density, there must be refraction at that boundary. So that is why when you are seeing that pin, it appears to be what? Shallow. Do we understand? So refractive index N is equals to real depth divided by what? Apparent depth. Is that clear? Then we can also be asked to find our lateral displacement, okay, or upward displacement. We can do that using a rectangular glass block. So I will show you how we can do that with a small illustration. I have this. Now, this is my normal. Okay, this is my angle of incidence. This is normal. What I'm going to do is to get my angle of refraction, which is what? R, right? If I get my angle of refraction R, if I decide to extend this incident ray, I'll go this way. Okay, then I have my emergent here. Now I can decide to measure the lateral displacement, that is from here to here. I will call it what? L. Or I can decide to call it what? D. Right? So in this aspect, you can be asked to find the lateral displacement or the upward displacement. Okay? Now, I will say the lateral displacement is equal to what? Real depth minus what? Apparent depth. Okay? Real depth minus apparent depth. Is that clear? For you to know how far it has displaced through the glass, that is lateral displacement. Okay? By extending this incident ray and the emergent ray, you can see the distance between them. Alright? That gives you a lateral or upward displacement or actual displacement. Is that clear? Alright, so the formula is real depth minus what? Apparent depth. Is that okay? So if you get the real depth and get the apparent depth, you can get the difference between them. That will give you the lateral or the upward or the actual displacement. Is that clear? Right. All right, we're going to be looking at a few examples on what I just explained. All right. So can we look at this question? A swimming pool is 2.1 meters deep. Okay, that is the real depth. When you look at it or when you measure it, you're going to see 2.1 meters deep. Okay, now if it contains water of refractive index 1.3, calculate the apparent depth of the pool. How do we do that? Real depth is equal to what? 2.1 meters. The refractive index is 1.3. Then the apparent depth, that is apparent depth is what you are looking for, right? So we say that refractive index is equals to real depth over what? Apparent depth, right? Okay, now since you are looking for this, cross multiply apparent depth is equals to real depth over refractive index. That is n is equals to what's my real depth? 2.1 over 1.3. Okay, that is apparent depth. Apparent depth. Okay, so let's divide by saying 2.1 divided by 1.3. So my answer becomes 1.62 meters. Okay, this question is straightforward and simple. They just gave us what? Our real depth, and they gave us refractive index. We are asked to use what? Find the apparent depth. Okay, so using the formula that refractive index n is equals to real depth over apparent depth. Is that clear? Right. Okay, the answer to the explanation of Sakwe is 1.2 centimeters. Okay, 1.2 centimeters. Okay, let's try and see whether we can get the answer. Let's check if you are correct. Okay, so let's solve. A measuring cylinder has a depth of 4.2 centimeter when filled with a liquid. Dropped inside it appears to be at a depth of 3 when viewed from above. Calculate the refractive index of the liquid. There's one thing you must understand. When something is said that when viewed, when a value is given as that when viewed, viewed is associated with your what? With your eyes. It's no longer the real depth, it is the apparent. Okay? Whatever you view is what the apparent depth, no longer the real depth. Now, this is the real depth of this measuring cylinder. So we have real depth to be 4.2 centimeter, apparent depth to be 3.5 centimeter. Okay, all right, we're looking for refractive index, which is n, and the formula n is equals to real depth over what? Apparent depth. Is that clear? Now this is 4.2 divided by what? 3.5. Okay, let's work it out. 4.2 divided by 3.5, so my answer becomes 1.2. Okay, is that clear? So the refractive index of this liquid is equal. Is that clear? All right, so the real depth is 4.2 centimeter. The apparent depth, anyone associated with your eyes is said to be apparent, is 3.5 centimeter. And the formula for refractive index is real depth divided by what? Apparent depth. Is that clear? All right. At Osoko, you are correct. The answer is 1.2, but it does not have unit as centimeter. Refractive index is a constant. Okay? It does not have unit. Is that clear? All right, let's go to the next one. right, so let's look at this example on the board. All right, so let's solve. A traveling microscope is focused on a mark on a table. If a glass block of thickness 18.0 centimeter is placed on the mark, by how many centimeters will the microscope be moved upwards so as to focus the mark once again? Let me go again. A traveling microscope is focused on a mark on a table. If a glass block of thickness 18.0 centimeter is placed on the mark, by how many centimeters will the microscope be moved upwards so as to focus the marks again? The marks once again. And we're giving the refractive index of glass as what? 1.5. Right? Now what are we looking for? By how many centimeters will the microscope be moved upward? That is upward displacement, or lateral displacement, or actual displacement. Okay, so we are looking for either of them. We are looking for lateral displacement, upward displacement, actual displacement. So the real depth, which is the thickness, it happens to be 18.0 centimeter. So we write that the real depth is 18.0 centimeter. Okay, now the refractive index is given as 1.5. Now for us to look for lateral displacement L, we don't even have the apparent depth. So we'll solve for apparent depth, okay, before solving for lateral displacement. And the formula is N is equals to real depth over what? Apparent depth, right? So what's my N, which is refractive index, is given as 1.5 is equals to what's the real depth? 18 divided by what? Apparent depth, right? I can say cross multiply apparent depth is equals to 18 divided by 1.5. Okay? So let's see what we'll have. 18 divided by 1.5, my answer becomes 12. So the answer is 12 centimeter. Alright? So for me to get the lateral or upward displacement, I will say L is equals to real depth minus what? Apparent depth. Okay? That is L is equals to 18 minus what? 12. Alright? By the time I subtract, the answer becomes what? 6 centimeter. Is that clear? Now let me do a recap by saying that the real depth in this question, that is the thickness of the block, is equal to 18.0 centimeters. The refractive index is 1.5. We're looking for lateral or upward displacement. We don't have it. That's what we're looking for. But before we find it, before we get the solution to it, we must also solve for the apparent depth. And what is apparent depth? We don't even have the apparent depth. Okay, so it's our formula. Refractive index equals to real depth over apparent depth. Okay, that is 1.5 is equals to, my real depth is given as 18 divided by what? Apparent depth. By the time you substitute, you're going to get the apparent depth to be 12 centimeters. Okay, so my lateral displacement equals real depth minus what? Apparent depth. And my answer is equals to 6 centimeters. Is that clear? All right. All right, so let's move to the next one. Oh, Osakwe, the answer is 12 centimeter. Okay, that is the answer to apparent depth. Okay, once you are done with that, you now proceed by solving the lateral displacement by subtracting from real depth, and the answer will be 6 centimeter. Is that clear? All right, let's go to the next one. All right, so we are looking at the concept of total internal reflection and critical angle. Now, look at this 3 diagram. Let me clearly explain it. We are talking about total internal reflection and critical angle. We are considering when light is traveling from glass to air. From glass to air. If you remember that in the previous explanation I did for refraction, you see that light travels from air to glass. But in this concept, light is traveling from glass to air. Okay? Now, let me do a small illustration. Now, if I have this, right? And this is a ray of light. This is air. And this is glass. How will the light move? This air is always less dense. So if light moves from air to glass, because this glass is denser than air, it's going to bend inside this glass this way. Did you get it? Why is it bending this way? Because glass is denser than air. So when light travels from one medium to another of different density, refraction takes place at the boundary between these two medium, which is here. Okay? But if light travels from glass to what? Air. Which one is denser? Which is denser? Glass is denser. So if light travels from glass to air, it's going to move what? Away from the normal. But in this one, the light moves towards the normal. That is this way. Okay? Because glass is denser. But coming to this one, the light will move away from the normal. That is this way. Is that clear? Okay, so let me proceed with my explanation. Let's assume the angle of incidence. This is I. This is I. And this is I. Okay? The angle of incidence here is given as 30 degrees. And then the light has to move from here. On coming to this boundary, what happens? It bends away from the normal because glass is denser than air. Right? Now, we now increase the angle of incidence here again. Let's say 60 degrees. What am I going to have? If I have 60 degrees here as the angle of incidence, it means that this angle of refraction that was here when I is 30 degrees is going to increase further. Now it came at this point, this level, this is B, right? So it has moved from here to here on this interface, making the angle of refraction to be 90 degrees. So the angle of incidence in the dense medium, when the angle of refraction in the less dense medium is 90 degrees, that angle of incidence is what is said to be the critical angle. Okay? So if you are asked what is critical angle is the angle of incidence in the dense medium, when the angle of refraction in the less dense medium is 90 degrees. Did you get it now? So when the angle of the incidence angle is equal to the critical angle, when the angle of refraction is what? 90 degrees. Is that okay? Now coming to this last one, if I still increase the angle of incidence to be 80, this ray was here when the angle of incidence is given 60 degrees. Then when it was increased again to be what? 80, what's going to happen in this last part of the diagram? The whole of the ray is going to move inside the glass. It's going to move inside the glass. Now we can now say that all the ray has been totally reflected. We can also say that total internal reflection has taken place. Do you get it? Because at this point, the angle of refraction is here. Now, if you increase this angle of incidence again, it will move from this point inside the prism. Do we get it? So you can say that total internal reflection has taken place. Okay? So if you ask to state the condition necessary for total internal reflection to take place, The number one is that light must be traveling from a dense medium to a less dense medium. What is a dense medium? A dense medium means that this is denser than this. So light must travel from this to this, and also the critical angle must be exceeded. Once we exceed the critical angle at this point, you can see that total internal reflection has taken place. Is that clear? All right. All right. So we're looking at the conditions necessary for total internal reflection to occur. One, light must be traveling from an optically more dense to an optically less dense medium. That is one condition. Then two, the critical angle must be exceeded. Okay? Remember that for total internal reflection to take place, light must travel from where? From an optically more dense to an optically what? Less dense. So it will move from here and it will go this way, right? And also, the critical angle must be exceeded for us to have, or for total internal reflection to occur. Is that clear? All right, so let's see a few examples on how we can apply the knowledge of this total internal reflection. Now we should note that at critical angle, our refractive index is equals to sine I over sine R, right? Okay, but at critical angle, this one is when the light is traveling from air to what? Glass. But at critical angle, light travels from glass to what? Air. Okay? At critical angle, light travels from what? From glass to air. Then this is sine I over sine what? Sine R. But we should note that at critical angle, the angle of incidence is equal to the critical angle, and also the angle of refraction is equal to what? 90 degrees. Is that okay? It's equal to 90 degrees. Now, we can replace it, and we should also know that, okay, let's just state it. This is equal to sine C over sine what? 90. And we know that sine 90 is equal to 1. If sine 90 is equal to 1, we can say that NGA is equal to sine C. But we must not forget that NGA is inverse of what? 1 over ANG, right? Then it's equal to what? Sine C, right? So we can say now, therefore, my refractive index ANG is equal to 1 over sine what? C. This is a relationship connecting the refractive index and the critical angle. So let me go again. At critical angle, my angle of incidence is equal to the critical angle, and my angle of refraction equals 90 degrees. I'm making reference to refractive index of block, which is refractive index of glass, which is ANG is equal to sine I over sine R. I is the angle of incidence, and R is the angle of refraction. At critical angle of incidence is equal to critical angle, okay? Then the angle of refraction is equal to 90 degrees. Now, if we substitute it into what we have, the sine R is equal to sine 90, and sine 90 is equal to 1, and we are left with this. GNA is equal to sine C. You know what is GNA? When light is traveling from glass to what? Air, which is inverse of ANG, right? That is equal to sine C. Now, because I want to make ANG the subject, I can say that ANG is equal to 1 over sine C. So this is the relationship connecting the refractive index and the critical angle. So you're going to put up small examples to see how you can understand the concept of refractive index and critical angle. Right. this diagram above, we are asked to calculate the value of the critical angle and the refractive index of the block. Now, for us to solve for the critical angle, we can call this C. Okay? Now, how do we get the critical angle? We can get the critical angle because this is already a right angle. Okay? So this equals to 90 degrees. So we go by saying 44 plus C is equals to what? 90 degrees, right? Now, the critical angle, which is C, is equals to 90 minus 44. It's going to give me what? It's going to give me 46. Let me confirm. It's going to give me 46 degrees, right? Now, that is for the first part, A. Then for the second part, for me to solve for the refractive index is equals to 1 over sine C, right? So N is equals to 1 over sine 46. Okay? So let's find out what is sine 46. It's our calculator. I have 0.719. So this is divided by 0.719. So my answer becomes 1.39. Okay? Do you understand? So in this type of question, this is air. And this is what? Glass. So you must remember that this is a question under critical angle. Okay, once you're dealing with semicircular prism, or once you're dealing with light moving from glass going out, even though it's bending opposite to what we already explained. Okay, then my critical angle is equal to what? Critical angle plus 44 is equal to 90 degrees. So this is 90 and this is 90. Okay, now I have to get it. I equate it to 90 and got C to be 46 degrees. Then the next thing is to say what? The next thing is use the formula N is equal to 1 over sine C. Then N is equal to 1 over sine what? 46 degrees. We got the answer to 0.17 and we divided to get the refractive index to be 1.39. Is that okay? Remember, it does not have units, it's a constant. Okay? Right. All right, so let's move to the next one. All right, so we're going to be explaining. I'm going to be explaining the refraction of light through triangular glass prism. Okay, this triangular glass prism is an equilateral triangle that all the sides are equal, 60, 60, 60. Okay, I'm going to explain the movement of this ray. When light is incident on this is our normal. Remember that normal is constant. Normal is a perpendicular line to the reflecting surface, this surface, okay, of the prism. Now, if light is incident, it's going to move through and refract inside here, okay? Once the light refracts inside here, they are going to view through this side, AC. They are going to view this side AC. Now, this happens to be my 2 points, P1 and P2, okay? If I just do experiment on this, how to carry out this experiment, draw the outline and label it ABC, all right? Then measure your normal, that is your 90 degrees on this outline. You just like, this is your protractor, okay? This point degrees, which is the normal, you are going to place it on this point. How do we get this point? You can measure from here to here and divide it by 2. Okay? So you can have a fixed measurement throughout the experiment. You divide it by 2, then place this line will be on this outline, and this point will be on that point we measured. Okay, remember I said you can measure from here to here. It might give you 4 cm. You divide it by 2, that is at 2. You make a point, right? Then put this protractor here to be on this point, okay, and measure your what? Your normal, which is this line. Once you measure your normal, you join this point, you join it, okay, and do an extension inside this prism. Then the next thing you're going to do is to measure your angle of incidence. When you measure your angle of incidence by putting your normal, your protractor back, and measure the angle from here to here, then you can put your 2 pins, P1 and P2, right? After measuring, just draw the line to join this point, then put your 2 pins, P1 and P2, okay? Then once that is done, replace your glass block, then come to this side to view. If these 2 pins are in a straight line and you view, you are going to see these 2 pins on the other side, inside the glass, okay? You are going to be seeing only one. That means this one you are seeing P1 and P2. Then you put your P3 and also put your what? P4, right? Once that is done, what next are you going to do is to join this is called emergent ray. Anyone your eyes is seeing is emergent, okay? You join these 2 points to this point, all right? Then you make out another normal. Using your protractor again, you make out another what? Normal. Then when you make out another normal, you join these 2 points of normal to have this. So you're going to get a set up like this, right? Now I'm going to explain the angle of incidence is the angle between the normal and the incident ray, all right? The angle of refraction is the angle between this refracted ray and this normal, all right? Then the angle of emergence is the angle between this emergent ray and this normal. Now, if we extend this incident ray inside and extend the emergent ray, they are going to meet or intersect at a point here. That is what is said to be the angle of deviation. If you are asked to calculate the angle of deviation, this is how you can get the angle of deviation. Is that clear? All right? Now, this refracting angle is the equilateral triangle. We can still measure refracting angle from here. This is R, okay? 2 interior angle is equal to what? 1 exterior angle. Okay, so this 2 is equal to the of which is equal to this, and this is equilateral triangle. The refracting angle is constant, which is 60 what? Degrees. Okay, so if the refracting angle is known and the refractive index is known, we can get the angle of incidence, okay, and we can also get what? The angle of deviation. Is that clear? All right, we can also equally get the angle of refraction. Okay, so A here is our refractive angle, I is the angle of incidence, E is the emergent angle, and the R is the angle of what? Refraction. Is that clear? All right. Alright, so if you are asked to plot a graph of D against E, this is the deviation, angle of deviation against E, you are going to get a curve of which may be asked to measure the minimum deviation. That is dm, right? You're asked to measure what? The minimum what? Deviation. And you should also note that the refractive index of glass, the angle of deviation, and the refracting angle, they are related by this equation. Let me say the refractive index the refracting angle and the angle of deviation is related by the equation. N is equals to sine A plus dm divided by 2 all over sine A over 2, right? Where N is refractive index, A is refracting angle, and dm is angle of minimum deviation. Then you should know that this refracting angle is constant, and since it's constant, is equal to 60 because we're dealing with equilateral triangle. All the sizes are equal. Once that is done, I will know the refractive index of glass, which is also constant, as 1.5. Now you can get the angle of minimum deviation. Is that clear? All right. Well, let's solve this example. question says, the angle of refraction R of a ray of white light from air through a triangular glass prism of refractive index 1.5 is 29 degrees. Calculate the angle through which the ray is least deviated. Now, how do I mean by that? They are giving us the angle of refraction R to be 29 degrees, and we are giving the refractive index N to be 1.5, and we have to find the angle of what? Deviation, right? Now, how do we get the angle of deviation? Remember our formula that N is equals to sine A plus dm over 2 divided by sine A over 2, right? But we don't even have what? Our A. But if you go back to our diagram, let me do a small illustration again. All right? You will now observe that okay, we have a ray. Okay. Right? This is my R, this is my R, right? And I told you that 2 interior angle is equal to 1 exterior angle, right? 2R is equal to what? Is equal to what? A. So because you're looking for R, and I divide both sides by 2, you know what it means? It means that R is equal to what? A over 2. Is that clear? R is equal to what? A over 2. All right. So let's proceed. Now, you can see that this R given is A over 2. Is that clear? If you want to solve for A, what are we going to do? What are we going to do? It's either we replace here as R, because our R is A over 2. We put 29. Right? Even if we still divide it or multiply, we still get the same thing as 29. Okay, so let's proceed. So I'm going to replace our A over 2 here as what? 29 degrees. Let's see if we are going to solve for this. But what is our A? R is equal to what? A. Therefore, my A is equal to 2 times what? 20, which is going to give me 58 degrees. Right? So let's go. What's my N? My N is 1.5 is equals to sine. What is my A? 58 plus dm, which is what I'm looking for. Okay? Divided by what? 2, right? Then it's equals to sine. What is my A? Sine 58 divided by 8 divided by 2. Is that clear? So we go by saying 1 over 5 is equals to sine bracket 58 plus dm divided by 2, right? Okay. Then when you divide, I'm still going to get sine 29, right? So we can say this is over 1, cross multiply. Let's cross multiply to get what we have. Sine bracket 58 plus dm over 2 is equals to 1.5 sine 29. All right, let's see what we have. Okay, let's say sine 29 equals this, multiplied by 1.5. I have 0.7272, right? right. Now if I have this, the next thing I'm going to do, I will carry this sign to the other side to make it a sine inverse, okay? But I'm looking for the angle of minimum deviation. So I go by saying 58 plus dm divided by 2 is equals to sine inverse of 0.7272. Okay? So I can say shift sine 0.7272. What do I have? I have 46.65. Okay? So I can cross multiply 58 plus dm is equals to 2 times 46.65. So what do we have? 2 times 46.65. Now I have is equals to 93.3. Okay? So my dm is equals to 93.3 minus 58, right? Minus 58. So my answer becomes 35.3 degrees. Is that clear? Right, let me do a recap. So we said that the angle of refraction R of a ray of light from Earth through a triangular glass prism of refractive index 1.5 is 29 degrees. Calculate the angle through which the ray is least deviated. So you're looking for the angle of minimum deviation. Alright, so we are giving the angle of refraction to be 29 degrees. The refractive index to be 1.5. Then the minimum deviation is what you are looking for. But we don't even have the refracting angle. Okay? But from what we proved that 2r is equals to a, right? Then from our formula, n is equals to sine in brackets a plus dm over 2 divided by sine a over 2. Now, if 2r is equals to a, then you can say that a is equals to what? What becomes our a? 2r. That is 2 times what? R. What's my r? 29, okay? So I got 58. Now, let's substitute into what we have. My refractive index n is 1.5 is equals to sine in bracket. What is my a? 58 plus dm all over 2, right? Okay, divided by sine 58 all over 2, right? Okay, so we have to divide this to get 29 degrees. Now let's do cross multiply 1.5 over 1 cross multiply this. And what do we have? We have sine in bracket 58 plus dm all over 2 is equals to 1.5 multiplied by sine 29. So we got that to be 0.7272. Now, what we're going to do next is to divide both sides by sine and also to get sine inverse of this. And we just did sine inverse of 0.7272 and it gave us 46.65. Now we do cross multiply by multiplying it by 2 and it gave us 93.3. Okay. Then the last step there is to make our dm the subject. This is what we are looking for. So we now said the minimum deviation d is equals to what? 93.3 minus what? 58. And it gave me the answer to be 35.3 degrees. Is that clear? So this is how you can use this formula of minimum deviation to solve our problem, right? Now, if refractive index of glass is known and the refractive angle is known, we can as well solve for the angle of minimum deviation. Stress. Is that clear? All right. right, so the last question for today. Let's solve the last question for today. I hope this one is clear. All right, so let's quickly look at this example. A ray of light is incident at an angle of 30 degrees at an air glass interface. Draw a ray diagram to show the deviation of the ray in the glass. Now, how do I mean? The second one, determine the angle of deviation. Now, let's just do a sketch to explain what they just said. Okay, so this is a rectangular glass block. All right. Now, this is giving us 30, that is angle of incidence. Now, this is normal, right? Now, this becomes my angle of my refraction. For me to get the angle of deviation, I'm going to extend this. Extend this incident ray to get the angle of what? Deviation. Is that clear? So this is how you can show the ray of light through the glass. Okay? Then the second question, this is my first question. Second question says I should calculate what the angle of deviation. How do I calculate the angle of deviation? I don't even have the angle of refraction. Okay? So what I'm going to do is to say that n is equals to sine I over sine r, right? Now, since I'm looking for r, I'm going to say Sine this is equals to sine I over n, right? To make it the subject, sine R is equals to sine 30, because I is equals to 30, divided by 1.50. Okay, so sine 30 is 0.5. I can say 0.5 divided by 1.5. So my answer becomes 0.33. So R is equals to sine inverse of 0.33, right? Okay, shift sine 0.33. My answer is 19.27 degrees, right? This will help you to get the angle of minimum deviation. So what's the angle of minimum deviation? D is equal to I minus what? R. So my I is 30 minus 19.27. So when my answer is going to give me 10.73 degrees. Okay, so this is how to solve this type of problem. Then you are asked to sketch, show the deviation. This is the deviation. Sorry, that is deviation. Okay, now if you are asked to state the lateral displacement, measure from here to here, you get the lateral displacement. Okay, now for you to get the angle of deviation, you have to use this to get the angle of refraction, and use that relationship to get the angle of deviation. Is that clear? Right. All right, we have come to the end of today's class. Thank you for staying and sticking to the end of this class. Like I always tell you, the more you learn physics, the more you understand this better. I will see you next time in the next one. Bye.